Okay. Now I had this little drawing, this schematic drawing. I'm going to share this separately so that you guys can look at it. I'm going to encourage you to practice drawing this out and recreating the steps of what's happening here. But I also want you to think about the big picture of what we're discussing. So sometimes students get lost in the weeds. And what we've discussed today is how we end up having negative 70 millivolts in a resting neuron. How did we establish that? How is the difference in the movement of sodium and the different gradients and forces acting on sodium and potassium, how do those come together to give us a negative 70 resting membrane potential? All right. So just to give an overview here of what we're looking at and how we put all those pieces together. First of all, we want to establish that the cell is more permeable to potassium, 25 times more to be specific. So in order to reflect that, we're going to have more potassium doors, which we can see at the top here, or more potassium channels, which reflects that increased permeability. The second thing we want to take into account is the chemical driving force for both of these ions, which is determined by the concentration gradient. And in order for us to establish the concentration gradient, we want to recall that the sodium-potassium pump is on the membrane of our cells, pumping potassium into the cell and sodium out. So that movement is what helps to create the concentration gradients, which is then what determines the chemical driving force. So because there's more sodium outside, sodium has a chemical driving force, which is into the cell, which we can see here. And because there's more potassium on the inside, potassium has a chemical driving force, which is to the outside of the cell, which we can see here. Now let's think about the movement of the electrical driving force, right? So now the electrical driving force comes into play, and because we now have a negative environment inside the cell, why do we have a negative environment? Because more potassium is leaving than sodium can come in, because there's more of a permeability for potassium. So now we end up having more negative on the inside and more positive on the outside. Now we can think about the electrical driving force. And because there's a more negative environment here, both ions want to get into the cell according to that electrical driving force, according to that difference in charge. Because they are both positively charged, they both want to get into the negative environment on the inside. So sodium has an electrical driving force into the cell, and potassium also has an electrical driving force into the cell. Now we combine the two forces, right, and think about our ECDF, our electrochemical driving force. If we do that, we're going to add the two values for sodium, which gives us a really strong force into the cell. While we think about this being a strong force into the cell, we also want to remember that there's a smaller or lesser permeability, which is reflected by a single channel for sodium here on this side of the membrane. So that is to say, although sodium has a strong force, there are fewer channels. On the opposite end, we combine the forces for potassium, which is in opposite directions, and we see that the chemical driving force is the bigger force. So we subtract the electrical driving force, and so now we have a weaker force for potassium moving out of the cell, but again, it has more opportunities to do so. So it has more channels, so it has a higher permeability. So as we think about these two ions moving according to their ECDF, sodium really wants to get into the cell, but it has fewer opportunities to do so, whereas potassium wants to get out of the cell, right? Doesn't really want to get out because it has a weaker force, but it has more opportunities to do so, right? And then after this system is at steady state means that the pumping of sodium and potassium by the sodium-potassium pump is being balanced by the leaking of these ions according to their ECDF. So we have that pump, leak system, which brings us to a steady state. And so there's no further net accumulation on either side. So the ions are still moving, but they're not accumulating. And after we get to that steady state, and let's say we were to put a voltmeter into this neuron at rest, at steady state, we would have a negative 70 millivolts value. All right. Okay. So again, practice drawing this out, practice going over these 5 steps of how we establish this negative 70, and we'll talk more about this. If you have questions, just try to write them down, and we'll begin class next week by clarifying any of those questions. All right, so here's just another reiteration of that. So it's the sodium-potassium pump along with the leak channels, right? And then all of that together in coordination with each other is how we get that resting membrane potential of negative 70. Now we want to think about where that resting membrane potential is relative to sodium's equilibrium potential and relative to potassium's equilibrium potential. So potassium is way up here. Potassium is positive 60 in terms of its equilibrium potential. Just to remind ourselves, this means that at positive 60, sodium is no longer moving, right? At negative 94, potassium is no longer moving. But notice when a cell is at rest, its membrane potential is closer to that of potassium. This is because potassium has more channels. So a resting cell, the membrane potential is going to more closely resemble potassium's equilibrium potential because there are more channels on the membrane for potassium than there are for sodium, right? Now, if we think about the electrochemical force for any of the ions, so sodium or potassium, we can compare the force or the magnitude with which they want to move. We can compare that to the distance that we are from that ion's equilibrium potential. Okay, I'm going to say that again just because I know that was a bit convoluted. So let's say we think about sodium. Sodium is really far. When sodium is at equilibrium, this value is very far from the resting membrane potential. What does that mean? This is the degree to which sodium wants to move when the cell is at rest, which is a really large value. And we saw that before. We saw that illustrated in another way by that really strong driving force wanting to get into the cell. The same is true. Potassium is relatively close to the resting membrane potential, so it's going to be a smaller difference or a smaller magnitude. And again, we saw that illustrated in a different way because we subtracted those values, right? We saw a weaker force for potassium to move out of the cell. So a different way to express that is to say that when the cell is at rest, there is a stronger push to move sodium because sodium's equilibrium potential is really far away from the resting membrane potential. But there is a weaker push to move potassium because potassium's equilibrium potential is relatively close to the resting membrane potential. All right. Okay. Okay. We're going to reiterate that same concept here again. So if we took the value and we subtract that negative 70 from negative 94, we get 24. This is the magnitude with which we want to move potassium, which is a relatively small value, 24 millivolts in terms of the difference in the membrane potential between potassium's equilibrium potential and the cell when it is at rest. In other words, there is a weak flow for potassium out of the cell, but the membrane is very permeable to potassium. Opposite is true for sodium. So like we said here, sodium moving in the same direction, both forces moving in the same direction, also because sodium's equilibrium potential is really far away from the resting membrane potential, we're going to add those two values together in order to get the overall magnitude with which sodium wants to move. And so that's going to be a really big value, right? 60 plus 70 gives us a really large magnitude in terms of the difference. How far is the equilibrium potential for sodium from the cells when the cell is at rest at -70? It's really far, okay? We're going to have to go from -70 to 0, which is 70 millivolts. And then we're going to have to go from 0 to 60, which is 130. So it's a really large magnitude with which sodium wants to move. And another way to express that is sodium has a really strong net force into the cell, but it has a relatively low permeability because it has fewer channels.